Hi, this is my video number 16. I'll continue with the example on solving volterra integral equation, a non-homogeneous volterra integral equation. For this case, we look at the how to solve the volterra integral equation using iterated kernel and to find the Newman series solution for the non-homogeneous volterra integral equation. And also we use successive approximation. Okay, so look at this example. Find the Newman series for the integral equation. Find the Newman series for the following integral equation. We have ux 1 plus x plus lambda integrate 0 to x minus t ut dt. Okay. Now, if you compare this with a standard form of volterra equation, so we find that fx is actually 1 plus x and k xt is x minus t. Okay, and remember that for the Newman series, we are basically we are looking for the solution of the form. We are looking for the solution of the form ux fx plus lambda m integrate a to x, where a is a lower bound for the integral, km xt ut I think ut dt, ut dt. Hope you can see this. ut dt, yeah, the end there. Okay, so basically we are looking the solution of that form. Okay, now first thing, of course, we need to find what km is. Here we have km, we need to find km. So to find km, we need to find it iteratively. So for the iterative kernel, we have iterative for the iterative kernel or iterated kernel. We have k1 xt. This is kxt. So we have x minus t. And to find the m terms of the kernel, we have integrate t to x, k x xz, km minus 1 zt dz. Okay, using that formula, we try to find k2, k3 until we obtain the general form of the kernel. So let's do this. So we have k1. We are looking for k2 xt. This is integrate t to x. We have kxz, so x minus z, and we have k1 here, k1 zt, so z minus t dz. Okay, for this you can use the integration by parts. Yeah, use integration by parts. I think I don't have to show you all the detail of the integration by parts. You should know those things. Yeah, just take u x minus z, then you can differentiate this with respect to dz, with respect to z, so you got negative dz, and you can take dv as z minus t dz, then you can find v is actually z minus t squared over 2. So using this, for the integration by parts, we have integrate u dv, this is uv minus integrate v du. Okay, so if you do this, what we have, that give you uv, this is x minus z, x minus z, and then our v is z minus t squared over 2, and then from t to x, and minus, we have minus integrate v du. So v and du is there, so we have integrate t to x du, that were du is negative, so negative, put it positive there, so we have z minus t squared over 2 dz. Okay, then this give you 0, so that part is 0. So because we have x, there's 0, t, that one is 0, so what left is those, integrate those things, you get z minus t cube over, you have 2 already there, over 3, so we have basically 3 factorial. Okay, so by doing this, basically you can see from here, this is k1 x minus 1, k2 you have x minus t, maybe you can do one more x3 to find the general terms, but from there I can have the general term already. So k3 xt, if you cannot see it, then do it another one, right? So x, so we have evaluate x of t, so this should be x, yeah. So x minus t 5 over 5 factorial, and so on, until you can find for the m xt, basically this is x minus t 2m minus 1 over 2m minus 1 factorial. Okay, then having obtained the general term for km, yeah, and then you can just plug into the form of the solution form that we are looking for, which is the Newman series, in the form of Newman series. Yeah, so if you plug in there, so what we have, the Newman series solution is given as ux is equal to, we have fx plus summation of lambda m of m from 1 to infinity, integrate a to x, where a is our lower bound of the integration, km xt, this is ft dt. Okay, so our fx is, we have identified this at the beginning here, yeah, as 1 plus x. So we have 1 plus x there, 1 plus x, and for this we have lambda 1 integrate, our a is 0, x, we have k1 xt ft dt plus x lambda, and we have lambda squared integrate 0 to x k2 xt ft dt. Okay, and we have lambda cube 0 to x k3 xt ft dt, and so on. And we still need this thing, even though you don't, because that's means the next term, and so on. Okay, so we need to evaluate and substitute everything in there. So we have this is 1 plus x plus lambda integrate 0 to x. Our k1 is x minus t. We have k1 xt, so we have x minus t, and then our ft is 1 plus t dt. Okay, and then plus that one we have lambda squared integrate 0 to x k2 ft, and k2, our k2 is where is k2, x tolak x minus t cube. Okay, and then ft, so our ft is 1 plus t x tolak t cube over 3 factorial dt, and for last term we have 0 to x 1 plus t, this is ft, and then x minus t cube 5th to 5th factorial dt, and so on. Okay, so you can solve this using, again, we use the integration by parts. So you can solve those, and then we end up with the, I just come up direct to what I have done. Okay, so we end up with 1 plus, of course you need 1 or 2 more steps there. 1 plus x plus lambda, so we have x squared over 2 plus x cubed over 3 factorial, plus lambda squared x4 over 4 factorial plus x5 over 5 factorial, plus lambda cube x6 over 6 factorial, x7 over 7 factorial, and so on. This is 7 factorial. Okay, of course you can write this in the general form. You can write in the general form, even though it's like not a really beautiful pattern. But if you can recognize this, if you consider the even order, we have x squared, x 4, 6, and so on, and as well we have x cubed for the odd, x cubed, x5, and x7, and so on. So you can write this as we have 1 plus x there, and then we have lambda squared, lambda cube, and so on. So all those things that give you m from 1 to infinity, that lambda m. Okay, so when m equal to 1, so we got lambda, m equal to 2, we got lambda squared, m equal to 3, we got lambda cube, and so on. But for this, we split into the even and odd power. So what we have for the odd power, we have x 2m. You can see here 2, 4, and 6. So I put it 2m there over 2m factorial plus the odd terms, odd powers, x3, x5, and x7 there. So you have x 2m plus 1, I think plus 1, yeah, m equal to 1, so you got 3, yeah, and 2, you got 5, alright. So we have 2m plus 1 factorial. So that gives you the solution. So obviously in this case we don't have basically a closed form solution. I mean, the closed form solution is that the summation of that series gives you some particular numbers, yeah, or particular terms. But we still, you cannot just leave it as it is. And if we consider lambda equal to 1, yeah, if lambda equal to 1, of course this will give you 1 plus x cubed over 2 factorial plus x cubed over 3 factorial and so on. That's give you the exponent. Then for the same problem here, if you find the resolvent kernel, for this problem, the resolvent kernel, okay, is given by try yourself, x t lambda. This gives you summation m from 1 to infinity. We have lambda m minus 1 km xt. Yeah, if you do this, you will got x minus t plus lambda x minus t cubed over 3 factorial plus lambda squared x minus t to the 5 and 5 factorial and so on. So even the resolvent kernel, in this case, we don't have a closed form solution. We don't have a closed form solution. So therefore, this is one of the reason why we use or we find the solution of the form of Newman series. Yeah. Now, let me give you another example. Just a minute. Okay, let me give you another example here. For the equation ux 1 plus integrate 0 to x xt ut dt. Okay, we find the a Newman solution. If compared with the general terms of the Volterra integral equation, what we have, our fx is equal to 1, our lambda equal to 1, our kernel k is xt. All right, and then we can find what is using iterated kernel. Iterated kernel, we have that k1 is equal to k xt. This is our xt is xt, and our km xt, we have written this many times, t to x k xz km minus 1 zt dz. Okay, so with that we can find k2, k3 and so on. Okay, so we find the k2 xt, that give you integrate t to x, our k xz, that give you xz, and k1 is and zt. So we have t, we have zt, right? That one is z, then we have zt. So we have zt dz. So this is so take out the term without z, so we have x t there, so we have xt, and z squared, so we have z cubed over 3. Okay, from t to x, that give you 1 over 3 xt, we have x cubed minus t cubed, or you can write this x 1 over 3 x for t minus xt4. Alright, and then you can find K2, you can find K3. If you find K3, try this. You got x3 is given as 1 over 18 x7 t minus 2 x4 t4 plus xt7. And then you can find x4 and so on. Now, then we can use the Newman series solution. Yeah, a Newman series solution. What we have using Newman series solution. Yeah, so we have ux is equal to fx plus summation m1 to infinity. We have lambda m integrate from a to x. Our a is lower bound of the integration, and then km xt ft dt. Okay, then from there we have fx. Our fx is 1 plus, we sum up, so we have lambda integrate. Our a is 0, so 0 to x. K1 is xt, f is 1, so we have xt dt plus lambda squared integrate 0 to x. That is a k1, then k2 is that 1 over 3 x7t minus 2 x4 t4 plus xt7 dt, and plus we have when m equal to 3, so we have lambda 3 integrate 0 to x. That one we have 1 over 18. This one is wrong, sorry. This should be k2, which is 1 over 3 x4 t minus xt4. Yeah, this one should be that one. And for this we have x7 t minus 2x4 t4 plus xt7 dt. Okay, if you proceed this, because the integration, I mean the function is not difficult, so you just do it yourself. You will end up with the series like it's not a standard series where you cannot find the general term of it. So x3 over 2 plus we have x6 over 2 times 5 times 8 plus 8 to 12 over 2 times 5 times 8 times 11 and plus so on. So this is the solution to our Volterra integral equation. Okay, so next again I will consider another example where how can we use the successive approximation in solving the Volterra integral equation, right? So we're done for this one. Now we're looking for how to use the successive approximation to solve the Volterra integral equation. So successive approximation, that we have un x is equal to, un x is equal to, we have fx plus lambda integrate 0 to x k xt un minus 1t dt, where u0 either given, or you can take fx as a u0, or otherwise it's given. Yeah. So let's say u0, I just give a general notation. Let's say just u0. Okay, let's say u0, just u0. Okay, as a general term. So you can consider this as fx, or if it given, then use the given one. Okay, now let's say example for this. Example, yeah. We want to solve, let's say our equation is given as u equal to 1 plus integrate 0 to x ut dt. Yeah, the function looks simple, but the solution isn't really simple. Okay. For this case, compared with the general form of the volterra equation, we have fx equal to 1, we have lambda equal to 1, and we have k xt, this is also 1, and our u0 given x, this is 0. Okay, this given in the question, so means that solve that with u0 x equal to 0. Okay, so having done those things, so if you substitute into that, yeah, that what we have here, so that give you un, basically un x is actually, our fx is 1 plus we have our lambda is 1, then integrate 0 to x. We have k is 1, and then un minus 1 t dt. Okay, then from here you can find u1, u2, and so on. You have u1 t, u1 x, this is 1 plus integrate 0 to x u0 is 0, so we have 0, and dt gives you 1. Okay, and then u2, for u2 x, that gives you, we have 1 plus integrate 0 to x u1, so u1 is 1, so we have 1 dt, that gives you, and a t from 0 to x, that gives you 1 plus x. Then you can find u3 x, this is 1 plus integrate 0 to x u2 is given here, so we have 1 plus x, 1 plus t now, t dt, right? This will give you 1 plus x plus 1 plus x plus x squared over 2. And then you can proceed this. If you find up to un x, that will give you 1 plus x squared over 2 factorial, and so on. X n minus 1 over n minus 1 factorial. Yeah, that for un. And therefore, the required solution is that ux, we take a limit n goes to infinity, unx, that 1 plus all those things x plus x squared over 2 factorial plus x n plus 1 over n plus 1 factorial, this is be dot 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 plus dot dot dot, okay, and plus dot dot dot, and this give you, if you recognize this series is the series for the exponent x. So this is the solution to the given equation here. You can, of course, you can check this if you want. You can check this. If you substitute this into the equation, the given equation, then you should get the right hand side equal to the right hand side. So that prove that your solution here satisfy the given equation. Okay, I have one more example. For the successive approximation here, so let's write that one. Let's say we want to solve the given equation is 1 plus 0 to x minus t ut dt, and given u naught x is equal to 0. So we want to using successive approximation. Successive approximation. Okay, so of course, first of all, identify, compare with the general form. Our fx in this case is 1, our lambda is 1, our kernel k xt is x minus t, our u naught x, the initial approximation or the zeroth approximation is 0. Then we have the general term of the successive approximation, that un x is equal to a general term, so fx plus lambda integrate a to x k what is it, kst xt un minus 1 t dt. So using this we can find u1, u2 and so on. Okay, so from there, let me write that. So we have u naught, we have that. So u1, our u1 x is, our fx is 1 plus lambda is 1, then integrate 0 to x, our k kernel x minus t, u naught is 0, so 0 dt give you 1. Then we can find u2. For u2 x, we have our fx is 1 plus our lambda is 1, integrate 0 to x, our kernel is x minus t, un, which is u1, our u1 is 1 dt. Okay, so if we evaluate those integral, so what we have, this is just 1 plus our dt, so we have xt, xt, this one is minus t squared, and then evaluate from 0 to x. So what we have is you have 1 over x squared, 1 plus x squared over 2 factorial. And as well, if you do for u3, okay, you will got, this is 1 plus integrate 0 to x k x minus t u to t, so we have 1 plus t squared over 2 factorial dt. And if you do this, we have 1 plus x squared over 2 factorial plus x4 over 4 factorial, and so on. And then from there you can find the general solution. Un x, basically we have 1 plus x squared over 2 factorial plus, here you have x4 over 4 factorial, so plus x. If you look at the power of this, or the power is even, so which means we have 2n over n over 2n factorial. Okay, then for the solution, of course, again for the solution, u, because we are looking for the solution, u is equal to u of x. You take the limit of n tend to infinity of u and x. So what you got this? Limit n goes to infinity, so we have 1 plus x squared over 2 factorial plus x4 over 4 factorial plus x 2n over 2n factorial, and so on. And the solution is, you find out. I don't have a solution for that. Okay, so with that example, I think I'll stop here for the example of basically how to solve the Volterra integral equation, how to find the solution of Volterra integral equation using iterated kernel, and as well as Neumann series and the approximate solution or successive approximation. Okay, so with that, I thank you. See you in the next video. Bye.